So the first part of the lecture will be really algorithms on trees. So, but not any kind of problem, but some hard problems. And what I mean by hard problem is that computationally hard problem, these problems we may not be able to solve these problems optimally. Say by optimally I will always mean, in good running time means polynomial time, right? But some of these problems can be solved really fast on trees and on fat trees. So for first we will learn an algorithm on trees, and then we will learn an algorithm on fat trees. Okay, so what is the motivation? So because most interesting graph problems are NP hard, many algorithms can be developed for special class of graphs, and many important classes of graphs are decomposable. We will learn the meaning of this word decomposable in some way, like trees. Okay, so that's what the motivation is. Let's consider the following problem. Okay, so what is this called party problem? And you have a problem, and you have to invite some colleagues for a party. And what is the objective? Our objective is that total fun factor should be maximized. And what is the constraint? Everybody should be having fun, right? So you want to invite people for a party, and you want everyone to be happy, enjoying, and you want to maximize, the total fun which you could have. So one constraint is this: do not invite a colleague and his direct boss. You will never have fun, right? At the same time, because the relationship are in a way that you will never have fun. So essentially, what it means is that because in most of the sectors or most of the companies, like this is a very hierarchical order. So you have some people at the bottom, some people on the top, and some people on the top. And basically, what you are looking for is that, so you have certain weights on the trees, on the vertices, basically how much fun factor the guy can have. And actually, our job is to find a maximum independent set in this graph. And what is a maximum independent set? Basically, it is a set of nodes such that there are no edges among themselves, right? So what is our job? Our job is actually, if you look at combinatorically, we want to find a maximum weight independent set on trees. And what I'm going to do is, throughout this talk, is actually going to make an algorithm for maximum weight independent set on trees and some fat trees. Okay? Okay, so let's make an algorithm for this problem. For example, what is a maximum weight independent set here? If these are the weights, this is a maximum weight independent set. Okay, so I hope all of you know about this dynamic programming paradigm, and so this is used for solving lots of problems where the sub problems does not depend on each other in a nice way. Okay, so how are we going to solve this maximum weight independent set problem on trees? Okay, so generally what happens is that in the maximum weight independent set in dynamic programming, somehow we break the problem into smaller parts. And for smaller parts, we have certain solutions or certain certain key things we remember, and we try to pass this to other sub-problem and utilize all these things to get our algorithm or get our solution. So for our purpose, let's so this is our tree, and there are nodes. By TV, we will denote the subtree rooted at this particular vertex V. Okay? So we are going to keep two things at every vertex. Some sort of Boolean thing. What is A of V? It just stores something about this vertex. A of V is maximum weight of independent set in the tree below here. So here. Okay, so we are going to keep two things, A of V and B of V. Okay, so what is A of V? Is a maximum weight of an independent set in the subtree rooted below, and what is B of V is a maximum weight independent set in TV that does not contain the vertex V. So we are just going to try to maintain these two things for every vertex. Okay, and how are we going to do this? We will do this from here, like bottom to top. So now if I have a root here, so what is A of R? It is going to be the maximum weight independent set for tree rooted at R. And what is a tree rooted at R? It's a whole tree, right? So what will A of R store? It will store maximum weight independent set of the whole tree. Now how are we going to compute these things? We'll compute these things from leaf to the root. So we'll go from bottom to the top. Okay. So what is our goal? Is to determine A of R for the root. Okay. So what is the method? So suppose, so think we have V and it has some children V1, V2, V3 and Vk. So we know already A of Vi's, B of Vi. So what we know here, we have been given okay, and what is our goal? Given these numbers, we want to compute A of V, B of V. What is B of V? Let's first see what is B of V. It's a maximum weight independent set, okay, which does not contain the vertex V, right? So if it does not contain this vertex V, then you can find the maximum weight independent set here, you can find the maximum weight independent set here in each of these small subtree and add them up, because a maximum weight independent set here does not interfere with the maximum weight independent set here, because there are no edges between the two subtrees of a tree, right? So that gives us small formula that what is B of V? Summation I equal to 1 to k A of Vi, right? That's a very simple formula. But now we have to compute A of V. What is A of V? Now what is A of V is representing? It is representing the maximum weight independent set for the subtree rooted at this guy. Now that maximum weight independent set can either contain the vertex V or it may not contain the vertex V. If it does not contain the vertex V, then that number is already stored in B of V. Now if it contains V, then we add W of V, but what else should we add? What is A of V1 storing? Sorry, what is B of V1 was storing? Right? It was storing the maximum weight independent set in this subtree which does not contain V1. Now the point is, the moment you include V in your independent set, you cannot include any of these guys in your independent set. But that particular information is basically saying what is the maximum weight independent set here which does not contain V1, what is the maximum weight independent set here which does not contain V2, which we have already stored in B's. So what is A of V is max of vertices without him, and if it contains, then you do W of V and summation I equal to 1 to k B of V, right? So the values of A of V and B of V can be computed in bottom up order, like the leaves are trivial, right? Leaves are trivial, right? Because suppose it is a leaf. What is A of V? The weight itself. What is B of V? Is 0. That's it. So now I can compute this for the leaf, and once I have computed this for the leaf, I can compute for every parent of him by knowing these values for all his children, right? So this is a very simple algorithm to do, what is that called? Maximum weight independent set on trees. And essentially, some variation of this or other can be used to solve many other NP-hard problems on trees, like dominating set, vertex cover, some R dominating set, and things like that. And even much more complicated problems, if you can do exactly by doing this kind of dynamic programming and keeping right set of things here. I mean, what all things do you need to keep so that you can compute something which is A of V will always denote an optimum solution below. So you need to keep enough set of things here by which you could use together to get a solution for the whole object, right? So you need to come up with some set of invariants which, if you have been given, you can compute the optimum solution with the help of this. For example, here B of V was that invariant which helped us to compute A of V. Okay, so we have seen one algorithm on trees. Okay, so what I'm going to talk about, that this algorithm is quite generic, and the same algorithm can be used not only for trees but many other kind of graphs, right? Trees are not in some particular example, but this algorithm itself could be used for various other structures which looks like trees. Okay, so as a running example to explain what I'm trying to do, or what I'm trying to explain the kind of graphs for which these problems can be solved in very similar way, we will use independent set as a running example. So I have forgotten the weights for now because it wouldn't matter. So what we have is a graph G, an integer k, and our goal is to find a maximum size independent set of this graph. So this is a decision problem. Is there a subset S of Vg of size k such that there are no edges between vertices in S, or find the size of maximum independent set of G. Okay? So we will just use this particular example to explain all what I'm trying to say. Okay. Okay, so to do that, I'm going to introduce a kind of graph which is called T-bounded graph. Now, what is a T-bounded graph? It's a graph with n vertices and at most T special vertices. Now, what is this T special vertices? Called X, which is subset of x1 to xt, and X is called the boundary of G. For example, this is my T-bounded graph. It's no special graph. You take any graph, okay? You can call some T vertex, you label them with some subsets of x1 to xt, and we are going to call this as a boundary, and that's it. These are called T-bounded graphs. So basically, you take any graph, you can make some T, at most T vertices special by labeling them 1, 2, or T, and that's it. So this is what I will mean by T-bounded graph, okay? So there is nothing special, it's any graph marked with some special x1 to xt, some at most T vertices with labels x1 to xt. Okay, so these are very nice graphs actually, okay? We will see how these graphs, or the graphs which we can construct by doing some operation of this boundary graph, will give us trees and various other things. Okay. So now let's try to suppose, think of this way, that rather than a one vertex here, okay, suppose somehow we had a graph which looked like something very different, okay? Imagine that you had a graph where you had some few vertex here, not one vertex, and you had some graph here, and what is the property? There is no edges between here and here. Okay? So these graphs could look like here, could see here, but they do not see, like there is no edge from here to here. The only way you can go from here to here is via these set of vertices. Okay? These are called separators in, or like what is a separator of single vertex? Called cut vertex. If you delete it, graph becomes several components. So look at the trees. What is the property of trees? If you delete any vertex, graphs, right? But it is possible that in graph I may not find a vertex of single vertex which can separate the graph, right? But I may be able to find set of vertex which could separate the graph. All right? So we will try to mimic this understanding that in a trees we have just one vertex which if I delete it gets separated. So we will think, oh, what is those graphs where wherever I look, whichever part of the graph you will give me, I have some small number of vertex which if I delete, graph has several components, right? So what is the property of trees? The property of trees is that you give me any subtree, I will find you some vertex which if you delete, graph will become it. So imagine a graph class where I generalize this from one vertex to this vertex, that you give me any subgraph, I will find you a small set of vertex, say 2, that if I delete these two vertex, graph breaks into, right? So what is our objective is to try to understand these class of graph which looks like trees, right? In what sense? In the sense which I just now told you, that in trees if I delete any vertex, graph becomes gets separated. Maybe there are some graph classes where not one vertex, but there are a small set of vertex which if I delete, graph becomes separated. Because if you remember, the most crucial observation for our dynamic programming was that if there are subgraph here and a subgraph here, and if I have a solution here, we can add them up. And how can you add them up? To be able to do that, it is important that there are no edge from here to here, and that is what we crucially used, right? If we had edge from here, we might find a cheap solution here, we might find an optimum solution here, but maybe there's an edge from here to here, and that will mean that they are not independent set. But the very fact that such edges were not there, it allowed us to compute solutions optimally locally here and pass them up to get a global solution. Okay? So just try to keep this in back of your mind, that this is what I'm trying to mimic. Okay? This little idea is what I'm trying to mimic, and how to give a proper definition to these kind of graphs. Okay? So that is what I'm trying to do. I mean, like by next 10, 15 slides, what I'm going to do is to really define this particular graph class, and how this graph class can look, and how can we make an algorithm on this kind of graph class. Okay? And towards that, I have introduced this notion of T-bounded graph. So look at your trees. Okay? I can think of them as a one bounded graph. There is one boundary. boundary in certain sense tells you that this is a way to go out from here to here. Like it's a boundary in a real sense, right? So here, every vertex here, when he looks back, looks below, that particular guy is a boundary to the outside. Okay? In that sense, I mean, so trees, we will prove that it is in some sense 1 or 2 boundaried graph. And what happens if we generalize this to largest number? Okay? Okay. So suppose I had such boundaried graph. Okay? So what is boundary is these numbers, like these are the guys. So in some sense, this part of the graph is going to interact with the other part of the graph via this set of vertices. Now the question which arises, what should be, suppose I wanted to still solve maximum weight independent set, right? Suppose I still want to solve maximum weight independent set problem, what kind of information do I need to store on this boundary that I will be able to do the kind of dynamic programming we were able to do before for maximum weight independent set problem, right? Look, so if you look before, it was a boundary. We kept certain set of information, and with the help of that set of information, we forgot the graph, right? We never, once we had this A of V here, B of V here, do we care what graph we have here? No, I can compute the information here with this information, right? So suppose now this part of the graph interacts here, what kind of information should we keep here so that I can forget this part of the graph, right? So that is what I'm going to do. Okay, so it's a very trivial generalization. So what did we try to store for the trees? We said, hey, let's keep a solution which contains this vertex or it doesn't contain this. In certain sense, that is what we were trying to do. Now what I'm going to say, hey, now what we will try to do, look at this. What is the best solution if intersection of maximum independent set from here is none, or it is x1, x2, or it is x2, x3, right? We have to keep all possible subsets because any maximum weight independent set could contain any subset from the boundary. We don't know, which could be used later in the algorithm. We don't know. But how many possibilities are there? 2 to the power t, all possible subsets of this, right? So what I'm going to do is the following thing, and I will tell you that why this set of information is good enough to compute things. So what I want to keep here, so the size of largest independent set I such that I intersection x is equal to some s, right? So what I want, so I am going to keep a table. Okay, so what is T of S going to store? T of S is basically going to store what is S? S is a subset of 1 to T, our boundary. Okay, and what I'm going to store at T of S, what is the maximum weight independent set in this graph such that its intersection with the boundary is exactly S. So for example, what is T of phi? T of phi means what is the largest independent set such that its intersection with the boundary is empty set. So what is the largest independent set here, which does not contain any boundary vertex? 4, right? 1, 2, 3, 4. Okay, so let's fill it. It's 4. What is the largest independent set which contains, say, x1? Let's see what I have next. Okay, what is the largest independent set which contains x1, x2, x3 in this part of the graph? What is the largest independent set which consists of x1, x2, x3? It cannot have, right? Because x1 and x2 has an edge. So I have put minus infinity, right? So I will just fill, for example, what is the largest independent set which consists of x2 and x3? Now we have selected x2 and x3, then clearly you can't pick any of these vertex, and from this triangle you can only pick one. So x2 and x3 is 1, 2 and some one vertex from a 3. So you just fill this table up. It's not very hard. Okay, so you can just fill this table up. Now the point is, okay, so what it tells us that for trees it was just enough this A of V and B of V. Now if I have such kind of boundary, then we just need a big table. That's it. Essentially what we stored here is actually this subset only, nothing more. Okay. Now, so this is the table which we would like to compute, which we would like to create. And now let me tell you certain operations which we can do on these kind of graphs. Okay, because I mean, if I want to construct this whole tree, I need to define certain operation on these boundaries, right? So what is that operation? So let me define the first operation, which we call introduce operation. So what I can do by this, I can start with some vertex, okay? So I have introduced this new vertex, say x4, but this guy is not going to have an edge here. It is only going to have edge where? With these boundary guys, okay? With these boundary guys, okay? So we add a vertex xi not in x to this boundary, and the vertex xi can have arbitrary neighbors in x. He can have any neighbors here, but he will not have any neighbors here, okay? So a new vertex can be introduced in the x side, okay? I have made some new vertex in the, okay. So like for example, now my boundary has become, new x has become the one which also consists of x4, right? So now I am going to tell you how that, suppose, let's go back, suppose I had a table like this, I knew this table, suppose, and some new vertex gets introduced, right? Then I need to do something to my table, right? Because I need a new table for new x, right? So we need to update my table. So let's see how we can update this table. Given that I have a table for the old x, okay? So given a table for the old x, we need a table for the new x. Okay, so here's the formula, nothing more. So suppose xi, and for our case, what is this? It is x4, okay, was introduced into x with closed neighborhood. It should be n of x, n of x4. We update the table as follows. So how do we make a new table? Okay, look at the new table T of s. We say, hey, T of s remains T of s if this newly introduced vertex is not in this subset. That's correct, right? I mean, what are you trying to do? You are trying to do that what is the largest independent set in the below graph such that the intersection with the boundary is this. Now if this guy does not contain the new vertex, then from outside you can only get the same number of vertex as before, because the newly added vertex is in the boundary. So if this newly introduced vertex is not of that particular, is not part of that subset, then we don't have to update anything, we remain. Second, now this newly introduced vertex is in S, but it has some neighbors in S, right? Then we put minus infinity, because how can a S having an edge among themselves can be, you know, enhanced or can be made into a big independent set, right? So we put minus infinity. Now, so now we have a case when we have S, this is our x4, and look at other vertex. Now what is the property? X4 does not have any neighbor here. Then what it is? Then you know that x4 only has neighbors here in the boundary. So the next, the independent set is, you remember the old table, we have computed S minus xi. We have in old table what is the largest independent set containing S minus x4. You take that, you added x4, and this is fine. You have not violated anything because this guy doesn't see any of those guys anyway. And so its local neighborhood is completely determined by what it sees in x, okay? So how much time will it take to update this table? If the size of the boundary was t, it will take some order 2 power t time, maybe some polynomial, okay? Okay, so that's a way to introduce a node. Now let me introduce another operation on this, boundary graph, which I call forget operation. What is a forget operation? It's nothing. So I have this guy, I want to forget someone. So forgetting someone means that I remove his special power. That is, I will not name him and remove him from the x. Like I will not treat him anything like anything differently. For example, suppose let's see how we can forget x4. It means I move x4 to the other side and I forget. So now I have only x1, x2, x3 as a boundary, right? So this is what I mean by forgetting. So you don't change the graph, you just take this vertex and you just unlabel him. Now you treat him like a normal guy, okay? Normal guy means the guy who does not have a label, and you remove him from the boundary. Now when you introduce a guy, the label set x increases by 1. When you forget a guy, then this label set decreases by 1. And now we should also know how to update this. We should also, like, I need to know how the new table will look like after I have forgot something. Okay, here x4, it is nothing, you know. So what is T of S? Like it is a max independent set for S, right? So look, so you have here, now look at any independent set here. Now you have forgot something. That independent set might not contain this x4 or xi, or it might contain x4. That's it. So if it does not contain x4, it is represented by T of S, because previously the vertex which we forgot is part of the boundary. Agreed? That was the part of the boundary. So it means when I say T of S, what did we represent T of S? It's a maximum independent set whose intersection with the boundary is exactly S. So if x4 was already in the boundary, then this S will not contain this x4. So the maximum independent set which we have computed is the maximum independent set without x4, right? Or maybe the max, now because this unboundaried guy has become a normal vertex, it is possible that the largest independent set in this graph may contain this guy, because it does not have any more special power, right? So let's go back. So now, for example, before this guy was x4. So now what I have to do, compute again. What is, so if you give me a subset, the largest independent set containing these guys from here and whose intersection is exactly this. Now I take x1 and x2. Before, this guy was not allowed because x4, if you notice, was here, right? But now that it has moved this side, it can be part of the independent set which we can take from here. So to do that, you already have stored that information. How? x1 and x, you also have stored what is the largest independent set which contains x1, x2 and x3 previously, or x4 previously. So that is why. So you have these two information, you take max of these two and you update, right? So still updating my table is easy, okay? So what we have seen is that I have, so let's recap here, that I told you that this algorithm for independent set is no special. I mean, we can introduce this notion of what is called T-bounded graph. I told you two operations, forget operation, introduce operation, and I told you how to do, if something can be done on this, then how to update this table on this kind of graph. Now let's look at what we have done actually. So basically, there's a notion called path width of a graph, which I am not going, but what is path width of a graph? Basically, it's a graph which can be constructed by the minimum boundary size needed to construct G. So path width of a graph is a minimum boundary size we need such that every graph using introduce and forget node can construct this graph. That's it. So this is what is called path width of a graph, is basically given a graph G, what is the minimum number of boundary we need such that I can construct this graph by starting from that particular boundary graph and either doing introduce operation or a forget operation. For example, let's see. This is path, right? How can you construct this graph? What is the minimum number of labels you need to construct this graph with the operations which I have defined before? Like starting from an empty graph, I want to construct this graph, okay, by some T-bounded graph, and either by doing introduce operation or a forget operation. It was abstract before, now an example. We should at least learn how to do it for path. Anyone is willing to come and help? No? What do you want to choose? First, okay. Okay. You can do anything, it's up to you. But at the end of the day, after all of the operation, I just need this path. Which one? Okay, so let's give them name at least. Okay, no, let's give them name A, B, C, D, E, F, G. Okay, and we will use 1 to T for the labels. Okay, so now you want to introduce this guy with. Boundary could have been empty for a graph, so you could introduce a node. So I can introduce A with a label 1. Okay. With what? Same label? Can I introduce B with the same label? Huh? So that's what. So whenever you use the boundary, you have to use the letters 1, 2, 3 whatever you can go, and I have written the vertex with ABC. That's the difference. So what should be the label for this guy? Label 1, you have given that. On the top I am writing label, so whenever I forget that label, I will forget that label, that's it. So what are you going to do? Are you going to introduce B with the same label? A graph, remember, no two vertex at the same time has the same label. So we are forced to make a label 2, and remember, when you introduce a node, you can give any adjacencies to the vertices with the labels, right? So if you go, what did I say? Right? Xi can have arbitrary neighbors in X, but to no other neighbor. So at this point of time, I can give it a label and I can get this graph, right? Because between A and B I can put an edge. Now what should I do? I can forget the label of 1. Okay? Now I can introduce what? With label 1. Okay? And I can give an edge between them. Right? I can alternatively do this. And so how many labels did we need? So what is the path width of a graph? As I told you, it's a path width of a graph is the minimum number of labels we need minus 1 for some reason. I don't know. It's okay. We can also think is the number of labels. So to construct this path, we needed 2 labels. Okay? As an exercise, try how many labels do you need for this stair? It's an exercise. Try for yourself. I mean, to just get a hang of these things. Okay? Okay. So I have defined you like one of the most technical things, which I at least used to find very hard in the beginning, which I still find, but in a really, so this is what I mean by that. I can construct this graph recursively, right? So imagine, so just for a minute, imagine, right, that, and also try to make for this graph, okay, for this this binary tree of depth 3. Try to construct like this graph by using this label operations, and you see how many labels do you need. Okay, and then try to see if you have a binary tree with depth L, how many labels do you need? Okay, okay, just for curiosity. Okay, so now let's go further and try to introduce more operation to this T boundary graph. Okay. And I have told you actually what I have told you now, that independent set can be solved in time 2 power p into n if a construction of G with p labels is given as input. If someone told you this construction of graph with these p labels, then you can compute independent set in 2 power p n time. The way I have actually explained you algorithm. This introduce, so in the beginning you have just one node, everything is easy. Next time if someone comes, you know how to update the table, so you can actually compute the maximum independent set of this graph in this much time. Okay. Okay, let's see. Okay, and there are many algorithms. Just to give you a flavor on this class of graph, you can compute independent set in 2 power p n time, dominating set in 3 power n time. If you are looking whether a graph is q colorable or not, where like 3 colorable, 4 colorable, these problems are NP hard on general graph. But on this class of graph, you can solve in q power pn. So for example, if p is 5 or 10, this is still constant. And if q is also constant, p is also constant. You can do max cut of a graph in 2 power pn. You can do some odd cycle transversal in 3 power pn. If you can find an Hamiltonian cycle of this graph actually, you can test whether the graph has a Hamiltonian cycle or not in time p power pn, right? So that is a bit more hard to do. And if you want to see whether graph can be partitioned into triangles or not, you can do in 2 power pn time. So just to tell you that independent set example was just one illustrative example, but there are many other problems which can be solved with doing something very similar to what I was trying to do before. Finding a path width of a graph, constant or non-constant. It's NP hard, NP complete. So in what sense you are asking? Getting? No, you cannot. So as I told you before, right? Given this decomposition, you can do this, right? So, but suppose I want to check whether graph has. So let's wait for the next slide. Okay. Hopefully, it will answer some of your questions. So what is this path width? It was actually introduced in 80s as a part of what is called Robertson and Seymour's graph miners project, and Bodlander and Clarks in 1996 gave an algorithm which can detect whether graph has a path width k or not in actually time f of k into n. So if you are looking for you want to test whether graph has, say, path width 10 or not, and you want this decomposition, then in f of 10 into n time I can do this. That 10 is horrible, f of k is horrible, but still. So it's like this f of k. So I can check. So this is the running time. It's not that bad. So for example, if you want to check whether graph has path width 10 or not, and you want to construct this path decomposition, then you might take 2 to the power 10 cube into n. But it is linear. We are computer scientists, so we should not worry. Okay. Okay. So it has some more nice things. For example, it has been used for various other purposes. For example, you can show that if a graph has m edges, have path width at most m divided by 5.769, and it uses very nice some spectral properties to prove these things. It is also known that 3 regular graph has path width m by 9 or n by 6. Again, it uses very nice something called max bisection and things like that. Now you can make a fast exact algorithms using this path width for max 2 CSP, counting vertex cover, dominating set, and blah blah blah, and several other things. Okay, so finally, let me introduce another operation on this T-bounded graph. So what we did? So we defined T-bounded graph. We defined 2 operations: introduce and a forget. And what did we get? We got something called path width. Now let's introduce the third operation. What is the third operation? Given 2 T-bounded graphs G1 and G2, the join operation glues them together at the boundaries. Okay, so it will just glue them together at the boundary. For example, so suppose we have been given 2 T-bounded graphs G1 and G2. Okay, so now we have this boundary. Okay, now what we are going to do? I want to join them. So how does the joining operation happen? If you notice what happened, look, we put x1 on x1, we put x2 to x2, we put x3 to x3, and if some label is missing, it's okay. I mean, we just leave that label, okay? And we take union of all the edges. So for example, here we did not have edge between x2 and x3, we have an edge between x2 and x3. And if there were some parallel edges, we can get rid of them. So you keep only one edge. So basically take union of these edges. So you put x1 to x1, x2 to x2, x3 to x3, and you take the union of edges which appears here. Okay? So this happens. That's it. Okay, now let's learn how to update the table here also, right? Remember, if I had been given a table for independent set here, if I have been given a table for independent set here, I need a table for both combined. Isn't it trivial? So what is T of S? I said, hey, what is this S1? Now, but independent set here and independent, there is no edge from here to here, right? So whatever independent set I can extend here and whatever independent set can extend here, I can put them together to make an independent set. But the only thing is there, S is counted in both sides, so you subtract S. That's it. And I can do this operation very fast in 2 power t time. Okay, so now I have also taught you join operation. And this is what is called tree width of a graph. Okay? It's a minimum boundary size needed to construct G from the empty graph, and then you use 3 operations: introduce, forget, and join. And I have told you that independent set can be solved even on this graph in time 2 power t. Okay. So now someone is willing to construct trees using these operations? Look, we computed path using this. Okay? So let's compute a tree. Not very big tree, okay? help me to construct this graph using these 3 operations, and let's see how many labels do we need. Any help? We can try to construct. So let's construct. I mean, it's okay to learn all abstractness, but we should also know how to do things at times. Like I have just made some 2-3 definitions, it's not too much. Okay, I help you people. I introduce A with 1. I with? Okay, I constructed I. Okay, 2 I, and you want to give an edge here. Okay, and what you want to do now? Forget? Forget 1. So we have, okay, now what? With label? With label? And now? Okay, now what do you want to do? Forget? You are not forgetting AB, you forget labels. Huh? Okay, now? So you want to introduce what? Okay, with what? Okay. And now I want to forget? Okay. What you want to do? Introduce J with operation, and you want to put an edge here. What?
We should do it parallelly.
I am just following you people. Is there something wrong going on here?
Yes.
What? Huh?
After ABI, we should try CDJ.
Okay.
And then we should join ABI and CDJ.
You know what is going to happen because of this? If you don't do this, no, it's okay. There was nothing wrong. But now you will notice that, okay, now do you want to forget 1 or something? What is going to happen if you forget 1 now? You don't able to join O here, right? So you have to keep this object, because if you want to construct this part of the graph, then you have to keep this guys. But if you are going to keep this guy and this guy also, and you want to construct this part of the graph, then you need another label. And that may not be the optimal way, right? So when you are only allowed to do, say, join and introduce, that is your exercise, right? You will see how many labels do you need. But now you have this extra power that you can also join objects. So maybe this was not the right way of doing it. Okay? So what is the right way of doing it? What do you want to do now? You don't want to introduce this. Okay? So suppose it doesn't matter. I have 1 here. Now what do you want to do? You want to construct? You want to introduce J, C, D. Okay, and what is the label here? It should be 2. Okay. Now what do you want to construct? You want to construct now M here, and put them together with the same label, right? So I can construct here. So maybe you can construct in a way that it's actually this is also 1. You can construct in a way that even this is 1. It's not big deal. Now you can introduce M with a label 2. You can give an edge here. And now I can introduce M with a label 2. I can add an edge here. And now I can do parity, put 2 and 2 together, and M, and I can do this. Okay, so you can keep doing this because of this. And how many labels do you need? Is at most 2. Actually, you need 2 labels. That's it. You can do this. You can try at home. It's not very hard. Okay. So in fact, you can construct any tree with 2 labels. Okay, and that is why it's tree width is, what is that called, is 1, because number of labels minus 1. Okay. So now more or less this is all that I want to tell you, but now let me show you some interesting thing. So I have told you how to find independent set also on graphs which can be constructed by these 3 operations in time 2 power t, where t is the number of labels. So this is also introduced as a part of graph minors, and Fellows and Lancaster in 1988 showed that you can actually recognize whether a graph has tree with t or no in f of t in n square time, but in this algorithm this f of t, if it was not a computable function. So it cannot be, this function cannot be constructed by any Turing machine, okay, deterministic Turing machine. But then in 90s Bodlander gave an algorithm which ran in time 2 power big O of tq time to test whether a given graph can be constructed with t labels or not, and actually it can give you this parse tree of this labeling, okay. If you look at Kleinberg and Tardo's book of graph theory, no, not this algorithm book, he or she gives an algorithm which, given a, if tree width of g is at most t, constructs with a 4t labels. It will construct you not with t labels, but if a graph can be constructed with t labels, it will give you a construction with at most 4t labels, and it takes much lesser time, something like 16 to the power t, okay. And this is there in the textbook itself. So, and there is also an algorithm which given on n vertex you can construct whether, so if your graph has small number of vertex, say some 15-20 vertex, you can use an algorithm which with respect to number of vertex runs in this much time and can give you this labeling tree, okay. Okay, so again you can do these kind of, you can solve many problems on graphs of bounded tree width also, and this is what I mean by fat trees, because we started with a tree and then we fattened it with the big notion of this t bounded graph. Okay, so it has the same application in several things, approximation algorithm, parameterized algorithm, blah blah blah. So what I wanted to do is, I have some 10 minutes at least, I should show you some non-trivial application of these things. I mean, if you don't understand this part of the lecture, it's okay. Okay, it is just to tell you that these things are very useful and has been used in variety of applications. Okay. Okay, so I'm going to just flash my slides for next 5-10 minutes. So if you don't understand, please don't feel bad. Okay, so the notion of extended monadic second-order logic, whoever knows logic, is like, it's a very powerful logic. It has some logical connectives like for all or for all. There's a quantification over over vertices, over subsets, and everything. Okay, for example, in this language, you can represent. You want to test whether the graph has a cycle or not, so you can say, you can start with there exists C subset of V, like these kind of things. For all V in C, there exists U1, U2 in C, U1 not equal to U2, blah blah, and you are basically saying that adjacent guys are adjacent, right? So how do you say that? If U1 is not equal to U2, then an adjacent of U1V and adjacent of U2V is true. When is this true? Can you at least read this formula and say what does this represent? In a given graph, what will this formula represent? It's a subset of vertex, such that for every vertex I am able to find two U1 and U2 in C, such that U1 is not equal to U2 and V is adjacent to both. Exactly. So this tells you that it has a degree 2. So every vertex has degree 2 in this. This is true if and only if graph has a cycle, right? Why not the set of disjoint cycles? At least does it rules out any disjoint cycle, set of disjoint cycles? If I start with subset of vertex for every, so if I have 2 cycles and if that is my C, then for every U1, U2, for every V in C, I can find this 2 and this. So it just tells you that it has a cycle, but this formula could also represent set of cycles, right? So
because anyway, you take any graph and there is a vertex, like a leaf hanging out from the cycle, then also this formula is false. So it's not different only.
no, that's no. But if that is, if look at that guy, if then where is the degree 2 for that guy?
So exactly, that's what I'm saying. That even though the graph is a cycle, the formula is false.
No, no, but this formula, if this formula is true,
Then the graph has a cycle.
yes, that's true. Okay. So anyway, okay. So what I want to tell you is that, okay, there's something called Courcell's theorem. Okay, you don't have to worry about this, but it's a great theorem. Okay. So, okay. So what it tells you, okay, don't worry. It says that any property which I can write like this, which I can write in this language, some language. What is the size of this? What is the size of this formula? Can you count the size of this formula? Like some 1, 2, 3, 4, 5, 6, 7, 8, 9, count this. That's the size of the formula. Okay? It's a constant size formula, right? I'm able to write whether a graph has a cycle or not by a constant size formula. Okay? Now, what does Courcell's theorem tells us? That look, if you have a formula which can be expressed in that kind of language, and suppose the size of the formula is mod f, then for any graph which can be constructed with W labels, there is an algorithm running in time. How much? F size of the formula, comma the number of labels into n for testing this property on graphs having this. What it means? That you give me a graph which can be constructed with say 2 or 4 or 5 labels, then I can test whether this graph has a cycle or not in how much size? Some f of the size of this formula, which is constant, my number of labels, which is still a constant, so it's basically in linear time. And there are many other properties which can be expressed in this language, like independent set, dominating set, cube coloring, max cut, odd cycle transversal, Hamiltonian cycle, partitioning into triangle, feedback vertex set, vertex disjoint cycle packing, and million other problems. So what it tells you that, imagine, we know how to construct trees with 2 labels. Okay? So now if someone asks you a problem in your exam, and if you can construct the whatever the guy wants you to find in some small formula, then you know that it has a linear time algorithm. At least you know. You may not know the algorithm which this algorithm gives you, but you at least know that there is such an algorithm. So now you can do a normal dynamic programming to construct it. So at least it tells you, okay, we are in a good shape, and this theorem helps us to solve many problems. Of course, I mean, we don't know how this algorithm works behind this theorem, but it tells us to identify whether the problem is solvable in linear time or not. So we can use this theorem for some sort of just verification purpose. Okay. So I think I'll just give you some small more example. So the fact a graph a tree with less than or equal to 2, or you can construct this with 3 labels. So tree is precisely the object which you can construct with 2 labels. Okay. What about objects which can be constructed with 3 labels? These are called something called series parallel graphs. Now, if you have a grid like this of k cross k, you can construct with, I think, k plus 1 labels. Try all this. I mean, I've given you some small exercise. Try them out to get them. And there are some other properties. Okay, you can show that it's a very nice property about these objects, that if you can construct a graph with 5 labels or 10 labels, then you can construct any subgraph of this with that many labels. You can also construct a graph which can be obtained by contracting some edge. Like, what is the contraction? You take an edge, you contract, and you delete self loops and all parallel edges. You can construct even this graph using the same number of labels. Okay? So this labeling operation is quite robust in that sense. Okay? Okay. So what is the tree width of k click? If you have a click of size k, you can just check that it actually requires k labels. You cannot do less than that. Okay. So I will not going to teach you all this. I had the slide how to use this for approximation algorithm, but it's already an hour and I don't want you to go through this grill. But it's nice things, approximation scheme. Okay, so let me come to my last slides. So we started with an algorithm for trees, a simple algorithm for hard problems. So started finding classes where we could use a similar idea. So we studied what? We studied actually algorithms and graphs that were tree-like, right? They could be constructed in tree-like manner. Well, most of the problems we consider are also easy on clicks, complete graphs. Most problems which we want to study, say, what is the independent set of complete graph? 1. Like on click. So Why not study graphs that are click-like? If we studied the problems on tree-like graph, why not study problems on click-like graph? Well, next time, not now. Thanks. Any questions?